Hi, I'm Roshan, and we'll be discussing Bitcoin transactions in this short presentation. These are all the topics we'll be covering in this presentation. So, what are Bitcoin transactions? Bitcoin transactions are the backbone of the Bitcoin network. They involve transfer of Bitcoins from one user to another through a P2P network. Unlike traditional financial systems, there is no central authority that uh, is involved in Bitcoin transactions. This makes them fast, secure, and low cost. How do these transactions work? When a Bitcoin transaction is initiated, it's broadcasted to the entire network, and the transaction is verified by the different nodes of the network using complex algorithms like the hash puzzle. Once the transaction is verified, it is added to the block in the blockchain. The blockchain is a public ledger that records all Bitcoin transactions. Each block contains a unique code called the hash that links it to the previous block and creating an unbreakable chain of blocks. What are Bitcoin transaction fees? Bitcoin transaction fees are very small amounts of Bitcoin that have to be paid to the miners uh, for including a transaction in a new block. Transaction fees are paid voluntarily by the sender to increase the speed of the transaction. A transaction that uh, has fees will be given more priority by the miner and will be mined first. In March 2023, the average transaction fees on the Bitcoin network was around 0.0005, which is around $20. How are Bitcoin transaction fees calculated? Bitcoin transaction fees are calculated based on the size of the transaction in bytes and not the amount of Bitcoin being sent. Bitcoin transactions can include multiple inputs and multiple outputs. So the size of the transaction depends on the number of inputs and outputs, as well as the length of the associated scripts. The size of the average Bitcoin transaction was around 600 bytes in March 2023. Why do these transaction fees matter? Bitcoin transaction fees matter because they are an incentive for miners to include new transactions in new blocks and to secure the Bitcoin network. Without transaction fees, miners would have very little incentive to include transactions in new blocks, which would make the Bitcoin network less secure and more susceptible to attacks. In March 23, the total value of Bitcoin transaction fees paid to miners was over 900 Bitcoin, which was equivalent to around $36 million, indicating the importance of transaction fees for maintaining the security and integrity of the Bitcoin network. Additionally, during these times of high network congestion, the transaction fees can increase significantly, causing delays and higher costs for users who want to send Bitcoin quickly and cost effectively. What are transaction scripts? Transaction scripts are small programs that are included in Bitcoin transactions to define the conditions under which the transactions can be spent. These scripts are written in scripting language, which is specific to Bitcoin and are executed by Bitcoin nodes when verifying and processing transactions. Transaction scripts are a key feature of Bitcoin protocol as they enable complex transaction types and implementation of smart contracts. Turing incompleteness and stateless verification. The Bitcoin script language is Turing incomplete, meaning that it is intentionally limited to prevent potential vulnerabilities and ensure security of the Bitcoin network. This limitation ensures that the Bitcoin script language is incapable of executing infinite loops or performing unbounded computational tasks, which could cause performance issues or create potential attack vectors. Additionally, Bitcoin uses stateless verification, meaning that the verification of each transaction is independent of any other previous transaction, making it easier for nodes to verify transactions quickly and without requiring a large amount of computational resources. Script construct, lock plus unlock. Transaction scripts are constructed using a lock and unlock method, um, where the lock script defines the conditions under which the funds can be spent, and the unlock script provides the proof that those conditions have been met. The lock script is typically included in the output of a transaction, while the unlock script is included in the input of the subsequent transaction that spends those funds. The most common type of lock script is the pay to public key hash, P2P KH script, which requires a digital signature from the private key associated with the specific public key to unlock the funds. Other types of lock scripts can include multi-signature scripts, time lock scripts, and smart contract scripts, which can enable more complex transaction types and use cases on the Bitcoin network. What is the P2P KH? It is the most common type of log script used in Bitcoin transactions. It involves the use of hash of the recipient's public key to create a locking script, which can only be unlocked with a digital signature from the corresponding private key. It provides a secure and efficient method for sending Bitcoin transactions, as it is relatively simple to implement and is widely supported by the Bitcoin wallets and exchanges. How does this work? To send a P2P KH transaction, the sender creates a transaction output that includes the hash of the recipient's public key, known as the public key hash, as well as the amount of Bitcoin being spent. To spend the funds, the recipient must create a transaction input that includes a digital signature created with the corresponding private key, as well as the full public key that corresponds to the PKH used in the output script. When the transaction is verified by a Bitcoin node, the script checks that the digital signature matches the public key, and if it does, the transaction is considered valid and the source of funds are transferred to the recipient's address. P2P-KH is a simple and effective way to transfer Bitcoin, and it is widespread. Its widespread use has helped to make Bitcoin transactions more accessible and user-friendly for the average person. Introduction to digital signatures. A digital signature is a mathematical scheme used to verify the authenticity and integrity of digital documents and messages. It provides a way for the recipient of a message to verify that the message was sent by the claim sender and has not been altered in transit. ECDSA, the elliptic curve digital signature algorithm, is a widely used DSA used based on the elliptic curve cryptography. Serialization of signatures, DER. Distinguished encoding rules is a standard for encoding structures that are used in X509 certificates and digital signatures. ECDSA are serialized using DER encoding, which is a binary format that contains the signature and other metadata. The DER encoding includes a header type, the length of the signature, and the signature itself. This is an example of a ECDSA digital signature. The script is on the left side and the output is on the right side. Signature hash types, SIG hash. In Bitcoin, transactions are signed using digital signatures to ensure the authenticity and prevent double spending. SIG hash or signature hash type is a part of transaction signatures that determines which part of the transaction data are signed. There are several SIG hash types available, each with its own unique features and use cases. SIG hash all. SIG hash all is the default signature hash type and signs all transaction data except for the input scripts and signatures. Once signed, signature cannot be modified without invalidating the entire transaction. This type is recommended for most use cases as it provides a high level of security and flexibility. SIG-hash single. SIG-hash single is used when only one of the output transaction is being spent. It signs all data up to and including the input being spent, but excludes any additional outputs or inputs. This type is useful for cases where the transaction output is expected to change in the future, such as in multi-party escrow transactions. SIG-hash none and SIG-hash anyone can pay. SIG-hash none signs all the transaction data except for input, signature, and output amounts. This type is used in cases where a transaction input is being removed, such as a fee bump transaction. SIG-hash anyone can pay signs only the input being spent, ignoring all the other inputs and outputs. This transaction is used in cases where a transaction is being modified to add or remove inputs, such as in a partial signature request. ECDSA math. ECDSA is a cryptographic algorithm used to sign messages and verify their authenticity. ECDSA relies on the properties of the elliptic curves over finite fields, which provide a high level of security with relatively small key sizes. Now we'll talk about the key generation process. ECDSA uses public key pairs for signing and verifying messages. The key generation process involves the following steps. First, select an elliptic curve and a point on the curve called the base point. Choose a random private key, which is a large integer. Compute the corresponding public key by multiplying the base point with the private key using using scalar multiplication. The private key is kept secret while the public key is made available to the others. The signing process. To sign a message using ECDSA, the following steps are performed. First, compute the message digest which is a fixed length representation of a message obtained during a cryptographic hash function. Second, choose a random number called nonce and compute a point on the elliptic curve by multiplying the base point with the nonce. Compute the x coordinate of the point and reduce it modulo the order of the curve to obtain value r. Compute the inverse of the nonce modulo the order of the curve and multiply it with the sum of the private key and the product of the message digest and R. Reduce modulo and the order of the curve to obtain a value S. The signature is the pair R, S. To verify the signature using ECDSA, the following steps are performed. First, compute the message digest of the original message. Second, compute the inverse of the S modulo um, in the order of the curve and multiply it with the product of the message digest and R. Reduce modulo and the order of the curve to obtain a value U1. Compute the inverse of the S modulo the order of the curve to multiply it with R. Reduce modulo the uh, order of the curve to obtain the value U2. Compute the point on the elliptic curve by adding the product of the base point with U1 with the product of the public key and U2. Finally, the signature is valid if the x coordinate of the resulting point is equal to R. The importance of randomness in signatures. The randomness used in signature algorithms is critical to ensure the security and uniqueness of each signature. Randomness prevents attackers from predicting or reproducing a signature without knowing the private key. If the randomness used in a signature algorithm is weak or predictable, an attacker can force signatures and impersonate the signer. The importance of cryptographically secure randomness. Cryptographically secure random number generators are necessary for ensuring the security of digital signatures. Non-cryptographic random number generators, such as those based on deterministic algorithms or system clocks, are vulnerable to prediction attacks. Cryptographically secure random number generators, such as those based on hardware random number generators or cryptographic hash functions, are designed to provide significant entropy and prevent prediction attacks. Now let's talk about Bitcoin addresses. Bitcoin addresses are the different identifiers used to send and receive Bitcoins on the Bitcoin network. They are a string of alphanumeric characters that start with 1, 3, or BC1. Addresses starting with 1 and 3 are the most common, while addresses starting with BC1 are newer and use a different format. For example, um, I've provided a, a picture of uh, a Bitcoin address in the right. Now, Bitcoin balance is the total amount of Bitcoins associated with a particular address. The balance can be calculated by summing up the total value of all the transactions that have been sent to that address minus any transactions that have been spent from that address. This can be viewed in the public blockchain. Other abstractions. Bitcoin also uses other abstractions such as inputs and outputs to manage transactions. The inputs are referenced to unspent transaction outputs um, that are used to fund the transactions, while outputs are the destinations where the Bitcoin transactions are sent. For example, if you want to send 1 Bitcoin to a friend, you would create a transaction with an input of 1 Bitcoin from your address and an output of 1 Bitcoin to your friend's address. The transaction would then be broadcast to the network for verification and inclusion in the blockchain. Conclusion. Bitcoin is a digital currency that uses a decentralized ledger called the blockchain to keep track of all transactions. Signatures, addresses, and balances are all important concepts in Bitcoin that help ensure the integrity and security of the network. The use of cryptography and randomness is critical to the security of blockchain of Bitcoin, and understanding these concepts is essential for anyone interested in using or developing the Bitcoin network. Thank you.